Hello and thank you all for joining us in today's webinar. Today's session is about the simulation and analysis of electromagnetic levitation application using EMWorks solution, which is EMS embedded inside Autodesk Inventor. So we'll start our session by giving a brief introduction about the levitation principles and their main applications. Then we'll see the design challenges that can be posed by these applications and the solution that can be used to address these issues and challenges, which is EMWorks solution. An example will be demonstrated of a Maglev system and how EMWorks solution can be used as well to overcome or address the main key design challenges related to magnetic levitations. A live demo and a QA session will be also covered in this session. So what is magnetic levitation? Is a method by which an object is lifted or pulled into the air with no support or direct contact. This is due to the applied magnetic field generated by currents or permanent magnets, which are used to reverse or counteract the gravitational pull or any other forces. It is highly advanced technology, especially the dynamic one, and it has various uses and applications. The common point in all applications is the lack of contact and there's no wear and friction. This increases efficiency, reduces maintenance costs, and increase the product lifespan. So the magnetic levitation technology can be used as an efficient technology in various industries. However, the technology most commonly associated with the term maglev in the mind of the general public is high-speed maglev trains. Magnetic levitation phenomenon is applied in wide range of applications like aerospace, nuclear, and military purposes, etc. So in addition to these applications, there are plenty of more innovative and futuristic ideas based on magnetic levitation, such as Elon Musk hyperloop, flying cars, and personal rapid transit, etc. So these ideas are being concretized faster thanks to some new used technologies like computer-aided design and simulation. So in order to design and create an innovative and efficient electromagnetic and electrodynamic levitation system, you may need to solve and overcome some of the key design issues. Like computing the magnetic fields will help to evaluate and identify the saturation of the steel that you use in your system. Calculating the eddy currents also is going to help you to evaluate some of the generated forces and also the electromagnetic losses like eddy current losses, ohmic losses, core losses, and so on. So this is can help you to evaluate forces, saturation, and losses. So these are important quantities while designing such system. Also, the magnetic forces are very important. So because the main thing of such application, so you have to evaluate the forces under different design scenarios, different situations, and also with different variables like the air gap, deviation, currents, speed, misalignments, and so on. So the use also of permanent magnets or electromagnets can be put in a specific configuration, so you can evaluate different configuration to analyze different output results. The combination of different materials, so you can evaluate your results by changing the material, so you can change the conductive or the ferromagnetic materials and evaluate your output data. The temperature has to be evaluated, so you have to evaluate the temperature because it's an important quantity that may affect your system efficiency. So these are the main key challenges or key design challenges that can be addressed while designing and creating efficient systems. So to tackle and solve the previous challenges, EMWorks proposes a solution that includes 3D electromagnetic simulation, so it can help you to compute the performance of your system, including coil parameter calculation, evaluate the magnetic fields in both frequency and time domain, or also static domain. So you can also use the software or the solution to compute the forces and the torques generated by your system, evaluate also the electromagnetic losses, eddy currents, and so on. So this is the 3D electromagnetic solution, which is embedded inside both SolidWorks and Autodesk Inventor, which is the software that we will demonstrate in this session. So these two powerful CAD solution can help you to like design whatever ideas in your mind. So you can also easily manipulate or change your geometry in a very fast way. So you can have like multiple or several iterations, so in very limited time. So the parametric studies offered by the solution can help designers to evaluate different quantities, including force results versus like geometrical variables like air gaps, misalignments, or currents or voltage. So you can evaluate your force or losses or magnetic fields versus these different variables. And this is like a complete solution for such applications. So you can use it to design your magnetic levitation system. So while you can compute forces, magnetic fields, also in the SolidWorks version you can use the motion coupling and also the temperature coupling, which is available for both SolidWorks and Autodesk Inventor. So you can evaluate the heat caused by different electromagnetic losses like winding losses or eddy current losses or whatever like hysteresis losses present in the system. So as an example, we are looking at like an electromagnetic levitation system used in semi and high-speed maglev trains. So it is composed mainly of F-type rail, guidance, and levitation magnets. So the 3D geometry of the model is created using Autodesk Inventor. So as explained, so our electromagnetic solution is embedded, integrated inside Autodesk Inventor. So you use the CAD of Autodesk Inventor for the 3D modeling. So you can design your system easily using Autodesk Inventor. So you can have like this one is like a section of your magnetic levitation system. So this represents like a planar symmetry. So in case of like 2D like simulation, we can just simulate a section of this system to save and increase the design iterations. So the levitation magnets are used to lift the train. So these like bottom electromagnet, and the left hand side or the left and right side magnets are added to maintain like some certain alignments of the system. So having like this native 3D geometry and that can be like parameterized during the simulation is an advantage. So you can change your geometry at any time. So you can modify whatever geometrical property there easily because you are using this native Autodesk Inventor CAD model. So you don't need to go to another CAD to change this, then import again the geometry. So it's inside the same platform. You can do this 3D modeling plus the simulation. So yeah, this is like a screenshot from the software. We can use the tree in the left. So that tree in the left represents the study or the analysis. So it has like the solids, which are the components present in the system. So like here we have two ferromagnetic bars made of steel tantan, and the coil is made of copper. Then using like magnetostatic simulation, we can compute the force on this F rail type rail part. So you can compute the force versus different parameters or variables. So here you can see that that's the electromagnetic simulation side, and if you just switch to the model, you can do your 3D modeling or change your geometry based on your electromagnetic results. So we look at some results. These are the magnetic results, different plots, different like type of plots. So you can see the fringe, you can see the vector plots, you can see the section with vector and fringe plots. So you can evaluate the field distribution, so you can understand on which area you need to maximize your field to get more maybe force, more attractive forces. So also you can evaluate the saturation, so and how you can minimize, reduce the saturation to avoid high electromagnetic losses like the hysteresis losses there. So this is one type of parametric simulation. So you can see how we can like parameterize. So since we are using the native 3D geometry of Autodesk Inventor, we can parameterize whatever geometrical variable or geometrical input in the system. So you can, for example, we parameterize here both like vertical and horizontal gap or distance, and force is being computed at versus value. So you can see the force versus vertical gap, how it increases or decreases when the gap becomes bigger. Also we see certain like deviation of the force when we increase the misalignment. So but this is like this lateral or horizontal gap or the force is less sensitive to this horizontal gap compared to the vertical one, because that one is the main like the main region that will help to get more field to attract that part on the top. So another example, which is computing the force versus different current. So you can change or parameterize the current and run your simulation versus like several current inputs and evaluate the force, basically the force results, but you also get the other quantities versus this input. So you can see here we are evaluating the force versus current and at different air gaps. So you can see 8mm gap, 12mm gap, and 16mm gap, and this again gives you a better overview on your system, so you can have like a better look at the system and how you maybe manage to increase the force or maybe reduce the power of your system. So this is like another example. So here we can see both levitation and guidance forces computed versus like deviation. So you can see the misalignment, distance is changing now, and we are evaluating both forces versus this change. And this is again using the parametric simulation. So another like example is or a type of simulation that we can use is the force computation versus different load material. So we can change this load and see how the material affects the force, and obviously there is an impact, and this is even it's sometimes is a minor impact, but sometimes is a big. So as you can see in the case of the steel 4140, we can see like a difference like in around maybe 3000 Newton compared to the M27, or even compared to the steel 1010, which represents like maybe around 2000 Newton. And this is can be critical in certain application and can be neglected in other applications. So this is why having such tool will help you to evaluate these kind of things without going and do real prototype, because real prototype is gonna cost you a lot of money and time, and you cannot cover all of these scenarios using prototype. So again, electromagnetic or computer simulation will help you to save time and come up with more innovative and efficient simulation. Now let's see some live demonstration into the software. So yeah, now we see Autodesk Inventor, on which we can find the electromagnetic solution or software provided by EMWorks, so which is a plugin or add-in to this Autodesk Inventor software. So this is EMS, as you can see here through this tab. EMS is the 3D electromagnetic software provided by EMWorks. So this is like an example of a magnetic levitation system. So you can see the magnet or the electromagnet on top of this system is made of two coils and ferromagnetic core, and a load on bottom of this system made of several steel bars. So this is the load at the bottom. So this through this analysis we can compute the electromagnetic fields and forces, especially the forces applied to this load or applied to each bar of this load. So we can like compute the total force or each bar force separately. So this is again the geometry. This is the model or the CAD tree. So you can change your geometry in real time, then go and do your simulation. Go back and come back to do the changes that you think that will improve your system, and again you do the simulation. And you can make this like automated by using the parametric option. So you can, for example, parameterize maybe the distance between these two bars or these bars, and the distance maybe between the load and your magnet, the thickness of a part, the length of a part, maybe whatever geometrical input or parameter can be linked to a variable and define it in the simulation. So you can evaluate your results versus the change of this variable, and you can include as many as you can or you want from these variables. So you can have like a combination of several variables, so you can evaluate your results versus the change of these different variables. And this will help you to get better understanding of your application and the performance of this device. So yeah, from the CAD we can switch to the simulation side. So here just a simple click. It's not like export something like a CAD file to another tool or change a tool. So it's just a switch between two tabs. This is the model, this is the CAD here. Then we switch to the simulation. You still see the CAD, but you just hide it. I mean, you hide this model side. Then again, so you see this is the simulation. Let's try to create a new study and see what we can find as analysis. So the analysis or the modules, so are the analysis that we can simulate, and they are like define it based on your output results or your problem. So here this is a magnetic problem. So the excitation, we know the excitation is a DC because these are electromagnets. So we can use magnetostatic to compute static magnetic fields, force distribution, the resistance of the coils, the DC resistance, inductance, and so on. So this can be done with magnetostatic. Electrostatic is something equivalent but in electric field region. So you can like compute the electric field distribution and so on when you apply a voltage for like electric device. So conduction, so this is like electric conduction, so you can like define current, voltage, and see the current distribution through your conduction system or conduction like path. So you can have like collection of conductive bodies or parts connected together. You put some excitation and see how the current is gonna flow through that system. AC magnetic is frequency, is the magnetic frequency solver in frequency domain. So you can compute your electromagnetic results in frequency domain. You define like just this frequency, and the software will compute the magnetic fields, the losses, and so on at this specific frequency. The transient is the most general solver that can help you to combine static, magnetostatic, and frequency analysis in a transient magnetic. So you can like do whatever excitation shape. So you can use sinusoidal excitation shape, which is similar to the frequency excitation, frequency domain excitation. You can apply DC excitation, which is similar to the magnetostatic. You can apply pulse, you can apply any random shape. But unlike, for example, magnetostatic, you can compute the losses here. So you can generate the loss, the ohmic losses, the hysteresis losses, and so on. So you can get the loss due to whatever excitation you apply. So this is the transient magnetic, and AC electric is something similar to the AC or equivalent to the AC magnetic. So it is electric field calculation but in a frequency domain. So frequency domain means that your excitation is supposed to be like sinusoidal excitation. But the simulation is just a steady state, so there is no like waveforms or signals versus time like in the transient magnetic analysis. So in addition to these electromagnetic solvers, we offer the possibility to couple these like modules or analysis to thermal simulation. So you can compute the heat generated because of ohmic losses. For example, here we do have like a DC current applied to the coils, so we get ohmic losses and we get some heat generated, whatever heat generated in these coils. So the software can help you to get the steady state or the transient temperature. So you can get the steady state, the final steady state temperature, or you can see like a variation of the temperature versus time through this coupling. And you don't need to like change or export or import some losses. So just it's basically automatic link between the electromagnetic solver and the thermal solver. So you need to apply some boundary condition like convection, maybe some specific temperature applied at specific maybe region of the system. Otherwise the load, which is the losses map, is going to automatically transfer from the electromagnetic solver to the thermal solver internally. So yeah, once you as I mentioned, so both options are available, steady state and thermal, and the transient thermal options are possible. So once you create your study, you'll generate like a tree or study tree. So it includes materials. So this is the material, so you apply your materials. For example, I want to apply copper to this, so I go to the library that comes with the software. So this is the library, the material library that comes with the software, and it is customizable library. You can edit the material, the existing material, and you can also add your own stuff there. So you can have like materials specific or special material applied or implemented in this library. So once you apply your material, simply just you select the material like this one, just one example here, copper for example, apply close. So it's gonna be applied here. You do the same for other materials. So you can do multi-selection to save time and so on. You can apply from favorite or recently applied material. I can apply from this menu. So then you apply all the materials, then you go and apply. Basically there is coil options, so you can apply your excitation. So I want to define, for example, a stranded coil. A solid coil is for like conductors or geometrically modeled coils, but for these kind of equivalent coils we can use this option of stranded or wound coil. Just let me, this option can help you to show height while do your selection. So I want to just show hide this cover, so we can see now the coils. So we select these coils, then apply select this face as an entry port, for example. So you can see this is the entry port of the current. So this is a loop, so it's a closed coil, so we need just the entry port, we don't need the exit port. Number of turns and current, so you can specify, for example, 1000 as a number of turns and 1 amp as input current. Just this is an example. Also there is option where you can define the wire gauge of your coil, so you can define the wire diameter or the wire gauge. And of course, so both current or voltage possibilities are available. So once you define this, so you select your coils and so on, select where you want to apply, for example, or compute force. I want to apply or compute force in this like part, not just in a separate bars. Then you apply this one. So these are like the main steps: material definition, coil definition, select just in case you want to compute force or torque. Otherwise you don't need to select or apply this option. Mesh, so you can use the default mesh settings. So there are like these default settings and so on to generate your mesh and get your results by just run this simulation. So it's gonna be fast simulation because it's not very complex thing. So I do have solve this example or a simulation. So here you can see the applied materials, different applied materials. Two coils are defined. Some mesh control in case I want to increase the size or maybe reduce the size of some mesh elements to increase the accuracy or maybe speed up the simulation. Then once it's solved, you can see there is results table. So the results table contains force, torque, resistance, and so on. But here we are mainly interested in the force. So you can see this is the force results. So this is the force along y direction, as you can see. So this is the force in y direction. You can look at x, y, z directions as well. So in case you have some misalignments and so on, you will see more relevant force in different axes. So resistance is the coil resistance, flux linkage, and the inductance. So this is the inductance matrix, so of these two coils. In addition to these lumped or tabular results, we do have also the 3D plots. So just double click, for example, this is an already created plot. So you can see the field distribution here. So you can see the field distribution. You can adjust the scale for a better visibility of the field. So different options like vectors. So here this is the vector plot. So you can change these options. You can go and change the vector options, do section clipping, iso clipping, and so on. You can evaluate the field at specific position, like between 2 points, along edge, along arc, along any shape. So you can specify or compute extract the field values at different positions. So there is BH applied current. So you can just double check the applied current density and the direction of the current. So you can see the vector of this direction. So to make sure that you are putting the current in the right direction. Yeah, so basically this is the software. So you can run this analysis, you can parameterize whatever geometrical variables and so on, and evaluate the performance, the behavior of your system versus different inputs and different scenarios, like changing the current, yes, and changing maybe some geometrical dimensions, changing the materials and so on. And this will help you to get better understanding of your system. As well, you can also add the coupling. So through the coupling to thermal, you will get the heat. So you can use at the same or using the same study, you will get both electromagnetic and thermal answer or response of your system. Yeah, so let's move back to our QA session and hear from you if you do have any questions. Thank you. Alright, so after finishing our live demonstration, we can move on to a QA session before wrapping up this webinar. So yeah, waiting for your questions. Thank you.